confidence interval for a proportion. Before we can make any inferences about a proportion, certain conditions must be satisfied. First, the sample must be a simple random sample from the population of interest. The population must be at least 10 times the size of the sample. The number of successes and the number of failures must be at least 10 each. Now what this means is that n times p has to be greater than or equal to 10, and n times 1 minus p, our proportion of failures, must be greater than or equal to 10. Our sample statistic for the population proportion is p hat. So based on the formula for a confidence interval, we have p hat plus or minus our margin of error. So how do we find the margin of error if it's not given to us outright? The margin of error is equal to the critical value, a number based on our level of confidence, and the standard deviation or standard error of the statistic. The critical value depends on the type of distribution that we have. We'll talk about normal distributions and t-distributions with our confidence intervals, but there are more than that. When the distribution is assumed to be normal, our critical value is found from the z-table or using the commands inverse norm or q-norm, depending on whether we're using a TI calculator or RStudio. If it's not normal for confidence intervals about means, then we use t-distributions, and that'll be discussed later. Our standard deviation or standard error when we're working with proportions is found by the square root of p times 1 minus p divided by n. However, when we're creating a confidence interval, we don't know the actual population proportion p. So we use the formula square root of p hat times 1 minus p hat over n. Finding the critical z-value for a confidence level. In RStudio, we'd use the q-norm command. Now, in a confidence interval, we're working with a symmetrical interval, symmetrical about the mean. So if I have, say, a 95% confidence level, we want this area right here to be 95%. That means the total sum of these two tails together would be 5% or 0.05. So each tail on its own would be half of that, 0.025. Inverse norm and Q norm give us the number of standard deviations that we are away from the mean based on our probabilities or areas to the left of our value. So if we're trying to find endpoints of this confidence interval, we're going to add 95% to 0.025%. And that's where the confidence level plus 1 minus the confidence level divided by 2 comes from. So with a 95% confidence level, our commands will be Q norm of 0.975 in RStudio or inverse norm of 0.975 on the calculator. If we had a 90% confidence level, then we would use Q norm or inverse norm of 0.95. 0.9 plus half of 1 minus 0.9. So let's look at an example. In the first 8 games of this year's basketball season, Lenny made 25 free throws in 40 attempts. What is Lenny's proportion of success? Well, for these 40 attempts, and we'll consider that a sample, his proportion would be 25 out of 40, which is 0.625. So let's find and interpret the 90% confidence interval for the proportion of all of Lenny's free throws. So first of all, for a 90% confidence interval, That means our confidence level is 0.9. We need to check our conditions. We'll have to assume that this is a simple random sample of his free throws, and he should have more than 10 times 40 or 400 attempts in all of his basketball career. We need his successes to be greater than 10, and we have 25, and his failures to be greater than 10. He would have 15 failures in this situation. So first of all, based on this confidence level, we need our critical value. Our critical value for proportions we're going to call Z star. And using the calculator, we would do inverse norm of 0.9 plus 1 minus 0.9 over 2, which again would be 0.95. Now to get to the inverse norm on the TI calculator, we're going to do second distribution 3. Now our area, that's what's in our parentheses, 0.95, and we keep our mu at 0 and standard deviation sigma at 1. And that gives us what'll round to 1.645. Next, we need our standard error, which will be the square root of our p hat times 1 minus our p hat divided by n. This comes out to be 0.0765. The margin of error is the product of these two values. And this comes out to be 0.1259. So our confidence interval will be our sample statistic plus or minus this margin of error. That gives us an interval from 0.499 to 0.751. Since this was a 90% confidence interval, we can say that we are 90% confident that the true proportion of Lenny's free throw success is between 49.9% and 75.1%. Sometimes we're asked to find the minimum sample size needed to produce a particular margin of error given a certain confidence level. When working with a one sample proportion, we would use this formula, the same one we used for the margin of error, our critical value times our standard error. But this time, if we're trying to find the sample size, we won't know n, but we will be given a maximum margin of error, and we'll solve the equation for n. So for example, it's believed that 35% of all voters favor a particular candidate. How large of a sample is required so that the margin of error for the percentage of all voters is no more than 3% at the 95% confidence level? Well, the 35% will be our P for our standard error, or standard deviation here. So we'll do 0.35 times 1 minus 0.35 divided by n. Our Z star value will be the inverse norm or Q norm of 0.95 plus 1 minus 0.95 over 2, which will be inverse norm or Q norm of 0.975. This value comes out to be 1.96. So our formula will be 1.96 times the square root be 0.65 when I subtract over n. And we want that no more than 3%. So we want it less than or equal to 0.03. Now we're going to solve this, and I'm going to do some division and cross multiplying here. So we're going to divide 0.03 by 1.96. And then we can square both sides. And that's going to give me 0.03 divided by 1.96 squared is greater than or equal to, now in my numerator I'm going to have 0.2275 divided by n. When I cross multiply, I'll have that n has to be greater than or equal to 0.2275 divided by 0.000234. So n has to be greater than or equal to 971.07. Now we can't sample 971.07. And n has to be greater than this value. So my next integer, since n is greater than, my smallest value for n would have to be 972. Always round up because we're looking for the n that's greater than or equal to this value.